Marcos. Can you hear me?
Hi, yes, I can hear you.
Okay, great. So yeah, we have both speakers here, and it is 12 o'clock in Washington. I will let the people in, and then I will start in 3 minutes. It's okay?
Okay, thanks.
Who is starting?
On my list, I have Francis first,
Okay.
and you the second.
Hi, Frankie.
Hi, Qusai.
Okay, it's 3 minutes past noon in Washington, in Eastern time. This is Marcos. Hello, everyone. Welcome to the Magnetosphere seminar series. Today, we have 2 early career seminars. So before we begin, I'd like to remind you this presentation is being recorded. So please keep your microphones on mute and send your questions in the chat box. I will read the questions at the end of each presentation. So our first talk is from Francis Staples. Please, if you could share your screen. And Dr. Staples defend her PhD. Dr. Staples defended her PhD at the Mullard Space Science Laboratory, University College London, in late 2021. Her expertise includes the dynamics of outer radiation belt and how solar wind and magnetopause interactions lead to magnetospheric plasma loss, with broader research interests, including how the solar wind produces changes in the near-Earth plasma environment, leading to space weather effects. She has specialized in multi-mission satellites and ground-based datasets. She began her postdoctoral research position at UCLA since January, working with Adam Kellerman on radiation belt modeling, assimilation, forecasting, and verification. And today she will deliver a talk titled Radiation Belt Dynamics from a Particle Perspective. Okay, it's all yours, Frankie.
Thank you, Marcos. So, hi, hello everyone. I'm glad to be talking here today. I'm going to be talking about how we use the dynamics of electrons in the outer radiation belt to kind of reverse engineer the physical processes which occur to create acceleration and loss from this system. And of course, thank you to my co-authors on this work. The research that I'll present has recently been submitted for review, so a preprint should be available soon, or you can email me at this email here. Okay, so the Van Allen belts are two rings of relativistic electrons and protons, which are trapped in Earth's magnetic field. They are very important because there are some satellite orbits which go within the outer radiation belt, such as geostationary orbits and GPS orbits. And these satellites are susceptible to the radiation in these regions. So it's really important that we are able to forecast and understand the variability in this region, which is nicely illustrated by this GIF on the right here. So for particles to become trapped in the first place, they follow three periodic motions. There's a gyro motion around the magnetic field. There's a bounce motion between two magnetic mirror points and a drift motion around the Earth. And the cumulative effect is that we get this drift shell illustrated by the squiggly pink line. If particles are trapped, then these motions are fast enough that the magnetic field is slowly varying compared to each motion. And if this is true, then the adiabatic invariants are conserved. So there are three adiabatic invariants which relate to each of these motions. And they're described by the canonical momenta of particles in their periodic motion. So the first invariant is described by the magnetic moment of a gyrating particle and is dependent on the energy and the pitch angle of an electron. The second invariant, K, is the integral of the magnetic field between two mirror points. And so this is dependent on the electron pitch angle. And the third invariant, which is phi, is the magnetic flux encompassed by a drift orbit. We usually use L star instead of phi, and this is inversely proportional. And this depends on the electron pitch angle. The talk is titled Dynamics from a Particle Perspective. And the reason that I use this title is because we're going to be using these adiabatic coordinate systems. So we're really relating dynamics to these specific energy and trajectories of the particles. And we use this in phase space density analysis. So phase space density is where we consider particles in a geographic space, and within that space we're considering individual momentum of the particles too. So suppose we have the number of particles dn within a small momentum range and in a small geographical space. This is described by the phase space density distribution F. So this function describes the entire phase space. In radiation belts, we use, we convert from this geographical space into the canonical momentum, the mu k and L star here. Now, this is really useful because of this Liouville's theorem, which essentially says, that so long as the adiabatic invariants are conserved, i.e. particles are following those closed drift paths, then the phase space density distribution won't change. That means if we do see any changes in this distribution, we know that there are permanent acceleration or loss processes ongoing in the system. So, as I mentioned, the radiation belts are highly variable, and we can see this in this figure, which is showing electron flux by the color for 3 different energy channels of the Van Allen probes. And this is a period of several months. We see sometimes there are some enhancements in radiation flux, which is associated with geomagnetic storms. But the periods that I'm going to really hone in on this talk are dropouts. And this is where we lose electron flux by orders of magnitude in very short time periods. So each dropout in this figure I've indicated by arrows, and they're often associated with enhancements in flux because they're driven by the same mechanisms, and these are changes in the solar wind. So how are we going to analyze these dropouts with phase space density? So there are 2 mechanisms which produce dropouts, and it's still debated about the contributions of either mechanism. The first mechanism is magnetopause shadowing. So this is where the magnetopause, which is the outer boundary of the Earth's magnetic field, becomes compressed by the solar wind. As it's compressed, it intersects previously closed electron drift paths, and electrons are subsequently lost into interplanetary space as they drift into the magnetopause. We can have this combined effect if there is high rates of ULF wave activity. Then particles can diffuse towards the magnetopause where they're subsequently lost. In the radiation belts, in phase space density, this presents as some extreme losses at very high L star. So in these right panels here, we're looking at a dropout event, which is produced by magnetopause shadowing. So there is some initial distribution of phase space density as a function of L star. And when we plot these kind of radial profiles of PSD, we're really looking at a single mu and k value. So the first and second adiabatic variant is constant. As the magnetopause is compressed, which is shown by this dotted line of the outer boundary moving inwards to low L star, any particle which was in this region of the phase space before is lost to the magnetopause. And then when the magnetopause relaxes, we are left with this characteristic peaked radial distribution, and the majority of losses occur at very high L star. Now, the other mechanism which can produce these dropouts in flux are emic wave particle interactions. So if there's a region where emic waves resonate with electrons, they can produce pitch angle scattering of those electrons. And cumulatively, there can be a diffusion of electron pitch angles into the loss cone. And then electrons are subsequently precipitating into the atmosphere as this occurs. Now, this is a highly localized process to where the emic waves occurs. So when we look at phase space density, what we expect is a highly localized loss process in the same region of interactions. So this should present as a minimum being created in the phase space density. And to be sure that this is a precipitation process, we need to observe this minimum to decrease over time. We need to see this decrease because we could have a minimum being created from several other processes. So suppose that we have magnetopause shadowing creating that radial peak, we follow that with an inwards radial diffusion, you'll result in a minimum. So for precipitation, this can add complication to our observations because we need to see the minimum being created over time. So we need to have several passes of a satellite through the radiation belt in order to create several snapshots of this minimum deepening. Now, as I mentioned, dropouts are extremely fast. So it's very difficult for us to capture in phase-space density this whole process because a satellite will take several hours to take a single profile of phase-space density across L-star. And this problem is really nicely demonstrated in Oliver et al. 2021, where they complete a simulation of a very fast inwards radial diffusion, which results in an acceleration in the radiation belt. So the simulation of the radiation belt is shown in these colored profiles. And then they send a satellite through their simulation and take measurements at each time. And the resultant profile is shown in black. And what we see is that the measured profile is not representative of the actual physical processes which occurred. So in our analysis, what we do to compensate for this is we're going to use a multi-mission observation of phase-space density to achieve the highest temporal resolution that we can. That is something that we published in a paper earlier this year, Staples et al. 2022. So this we completed a radial analysis of phase-space density in this storm, September 2017. And we concluded that magnetopause shadowing was the dominant mechanism of electron loss during the dropout. So what I'm going to present now is an updated analysis where we look in more detail at the precipitation effects during the same event. Okay, so in September 2017, in the solar wind, there are several interacting coronal mass ejecta, which result in these extreme compressions of the magnetopause, which is shown in this panel C, which is the subsolar magnetopause. And we measure the magnetopause being compressed within geostationary orbit. So we know for sure that the magnetopause should be affecting the dynamics in the radiation belts. There is a geomagnetic storm, and during the main phase of this storm, there is a dropout in the radiation belt. So this bottom panel is showing this phase-space density by color for a specific mu of 1000 MeV per Gauss and K of 0.1. And this is the multi-mission data set. The data that we used to create this phase-space density are the Van Allen probes, GPS, GOES, Themis, and MMS. And we're using the T89 magnetic field model because we did some testing and found that right at the period where we see the dropout, this was the most accurate model that we tested. So we then create some radial profiles of PSD to complete that radial analysis. So if we look at this gray shaded area, this is our pre-storm PSD. So that is in each panel, the gray line. And then we're going to take our time periods, which are indexed by these colored lines here. So we're looking at PSD as a function of L star. And in each hour, we're finding that the majority of PSD is lost at very high L star. And we're creating these radial peaks in PSD. So if we refer back to our schematic that we showed earlier, this is characteristic of magnetopause shadowing. However, during these 4 hours, we observe some very significant emic wave activity in the Van Allen probe emphasis instrument. So over these 4 hours, I've just got a schematic of where the Van Allen probes is so we can visually imagine it. And here is a sample of some of the emic waves that we observe. There are a strong enhancement in the helium band emic waves, which we can see by this increased wave power, very close to the helium gyro frequency, which is this white dotted line. And there are also some significant hydrogen band wave activity too. Now, through the whole hour, we see some variations in the different wave bands and how strong the emic waves are. And we take a selection of wave bursts to estimate pitch angle diffusion coefficients. So we do this to try and understand if the electrons are interacting with these observed emic waves, and if this is going to produce significant losses. So on the left here, we have these estimations of pitch angle diffusion, which is shown by color, for the 2 different wave bands. We've got the hydrogen wave band on the left and helium on the right. And we find that there are unusually low resonant energies between the electrons and the waves, down to hundreds of kilo electron volts. And we also find that particularly for this time period, which is between the 2 dotted lines here, the diffusion coefficients are extremely high. We would expect that electrons could be diffused on the order of seconds if they are already near the loss cone. So we're going to convert this data into the mu-k coordinates so that we can compare to our phase-space densities. So what we have is the minimum resonance with either wave band, which is shown by the magenta colors, and this matches to where this minimum resonance is here in these diffusion coefficients. And then we're also plotting the maximum diffusion due to both wave bands by this yellow line here. So this will match where we get the highest diffusion coefficients between the 2. And we complete this for that dropout period. So I showed these panels earlier where we were doing the radial analysis for mu of 1000 MeV and a K of 0.1. But now on the top here, we're looking at just Van Allen probe B observations of the change in phase space density. So change in phase space density of DF, and this is comparing the PSD observed during each panel to that pre-storm PSD, which is the gray shaded line earlier. And we're also, each panel is now a 30-minute interval of Van Allen probe B observations. We're showing it at a very wide range of mu and K, the first and second adiabatic invariants, whereas these radial profiles are fixed. So I say the radial profiles are fixed, but so mu is 1000 MeV, K of 0.1. So this will correspond to this box here in our figures. So what we observe is that the minimum resonance between the emic waves and the electrons is really defining where we observe losses. Below minimum resonance, we're seeing enhancements in PSD, and above minimum resonance, we're seeing losses in PSD by these blue colors. And this occurs throughout the Van Allen probe B observations. Even more interestingly, at the beginning of the dropout here in these left two panels, the white crosses are showing where we're observing maximum PSD loss as a function of mu and K. So where we're observing the most losses to the radiation belt is aligning with our estimated maximum diffusion rates. This does vary as we go through the period, and we think this could be a hysteresis effect with the changes due to pitch angle scattering could be take a longer time period to occur. So maybe we don't see this alignment here because of that. Okay. So then the question is, that is strong evidence that emic waves are driving electron loss during the dropout. Why don't we see a radial minima being created? We think this is because this precipitation is occurring at very high L star near the last closed drift shell. So we're having this composite effect of two loss processes occurring at the same time. So we'll have, suppose, a minima being created by that precipitation loss, but the last closed drift shell is intersecting where we would expect to see that inflection point. And when the magnetosphere relaxes, what we're left with is a peaked radial distribution, which is characteristic of magnetopause shadowing. So to conclude, I'd like to emphasize that when we do radial analysis of these peaks and minima, it is very hard to represent simultaneous processes at the same time, and we could be misinterpreting the actual physical mechanisms which are occurring. So to combat this, I really think that we should be doing some holistic analysis of the radiation belts. So this means that we look at the entire phase space, including mu, K, and L star, as well as looking at the properties of the drivers of loss. So that would be at using wave observations and looking at the outer boundary of the magnetosphere. And the final thing that I want to emphasize is that when we only use phase-space density observations, we can't quantify how much either of these processes is contributing to that dropout. So really, this is something that needs to be reconstructed using modeling efforts and further analysis of the drivers themselves. Okay, thank you.
Thank you. Thank you very much. Very nice talk. We still have time for questions. First is from Lane Wilson. He wants to know which spacecraft were used for your solar wind input.
We use the combined Omni data set.
Okay. And then other questions is from Elizabeth Antonova. Why the Tsiganenko 1989 model was selected for the PhD calculation?
PhD? PSD? So we looked at the magnetic field observed by GOES and by the Van Allen probes. So when we, particularly with L-star, it's important to accurately predict the magnetic field at high radial distances for the for the L-star computation to be correct. So we compared several different magnetic field models to those data. So we compared the Sigonenko storm time model in the 2003 paper, as well as dipolar field models, the T89 model. And we found there wasn't a huge difference between the storm time Sigonenko model and the T89 model. And it was kind of hard because the GO spacecraft are near the magnetopoles. But we did in the end decide that Sigonenko 89 was the closest during that dropout period, not during the whole storm, but during that dropout period. The T89 was closest matched closest to the measurements of the magnetic field in those regions.
Okay. And okay, I have a question. And do you also use the Tsiganenko to determine the magnetopause location, right?
The magnetopause location, we use the Shu magnetopause model when I showed that figure where we're looking at all the panels, but really during very compressed times that can become inaccurate. So we use measurements of satellite crossings of the magnetopause there. So we have GOES crossings, so we know for sure that the magnetopause was within geostationary orbit at that time, but that we also have a set of Themis crossings as well.
Okay, so that the location is just for the standoff location.
Yeah.
Okay. Okay. Thank you.
Thank you.
Thank you very much. Let's move on to our next. So our next talk is from Qusai Al Shidi, who came to or went to the US in 2008 to pursue a career in physics. They graduated with a PhD in physics at the University of Massachusetts, in which they developed a solar chromospheric simulation from scratch. Qusai now works at the University of Michigan and uses the space weather modeling framework to study energy transfer from the solar wind to the magnetosphere, as well as studying how well we can simulate the solar wind's effect on ground magnetometers, which is the subject of the talks today. Please, Qusai.
Yes, 1 second. Can y'all see my screen here?
Yes, we do.
Okay, okay. So thank you so much for the introduction. So today I'm going to talk about simulating from a solar wind input all the way to ground magnetometers. And my interest is how we could validate the models in doing this and whether the models can simulate this whole process, which is a highly coupled process. And the solar wind to ground magnetometers means a lot of different regimes of physics. So we'll get into that. So what are the goals of this study? We need to be able to see if we can simulate ground magnetometer perturbations. So here I'm talking about perturbations specifically and not dBdt, and I'll explain why later. And we will also use all magnetometer observations that are available from the SuperMag website. Now, what is SuperMag? If you go to SuperMag over here, you will see that it has data from ground magnetometers all around the world. If you click on download data over here, you can find you can download the data yourself. It's freely available. That's how I was able to do this study over here. They have 1 minute data resolution. Excuse me, I will need to reopen that. Yeah. So, and also to run as many storms as possible. So in order to study whether we can simulate the magnetometer perturbations, we need to have a big data set. Usually validation of this kind has been done with fewer simulations, usually fewer storms, I mean. So usually like around 5 storms or so. But with this, I ran around or over 100 storms from 2010 and 2019. So let me first explain the experimental setup. So this is mainly explaining the space weather modeling framework and in its geospace configuration. It's using the exact same operational setup from the Space Weather Prediction Center. So if I click here, you can see that this is the Space Weather Prediction Center website from NOAA. And you can see they are themselves using the geospace model of SWMF, that is the acronym, to study the different magnetic perturbations around the globe. So they themselves are using this for forecasting and that kind of stuff. And this is what it looks like simulated. So the point is to use the same operational setup because we want to see if using this can give good enough results. We could have a better, more scientific setup because this has a lower resolution than you'd expect for a scientific study. But for this, using the operational setup would be best because we want to be able to predict in advance. We want to be able to forecast. So we want to have simulations that are faster than real time. So this modeling framework is a coupled framework. It's coupled between a few things. So the first model is, or the biggest, the one that has it spans the most regions, is BATSARUS, and that's an ideal MHD model. So this simulates the solar wind and most of the magnetosphere. That is also coupled back and forth with the Rice convection model. And that mainly is to study the ring current or to have ring current effects in the magnetosphere. So it's an inner magnetosphere model and has its bounce average kinetic model, and it has also currents. And the currents are supplied back and forth to the Ridley ionosphere model. And this model is an electric potential solver. So it solves a Poisson equation with conductivity. And the conductivity used here is an empirical model derived from the Amy method. So yeah, so the storms. So a collection of over 100 storms from 2010 to 2019, because that's the things available to me when I started this. The storms were chosen based on the SIMH, or the disturbance time index, dipping below -50. So a good storm would dip below -50 nanoteslas. It could go to -100, but whenever we see a storm going below -50, we will say this is a geomagnetic storm, and we will run it. And there are over 100 between 2010 and 2019 that we found to simulate. And we'd have a virtual magnetometer grid of all the magnetometers available on SuperMag database. This is around 300, if I'm not mistaken. So it's quite a few. And we will, for the output, we will have a 1-minute cadence of delta B for all stations. I haven't mentioned the input, but the input will be the data from Omni for the solar wind. So the input is the solar wind, and the output is the virtual magnetometer perturbation. So a lot of people who are interested in ground-induced currents or geometrically induced currents are interested in dBdt, but we're looking at all stations. And the stations in the equatorial region aren't as concerned with dBdt, and they usually are contributing to the measurement of sim age, for example. So, and that's a delta B measurement. So in order to be more generalized, and delta B and dBdt are highly correlated anyway, and in order to generalize the study, we just go for delta B in this case. Now, how is this calculated? So I mentioned before there's an empirical conductivity model, and the Ridley ionosphere model solves the potential. So this is going to be on the surface of the Earth. And by surface, I really mean ionosphere, but that's as far down as the simulation goes. And the magnetic field perturbations are calculated through Biot-Savart integrals. So the Biot-Savart integral, and it uses output from the Ridley ionosphere model and BATS-RS to find delta B. If you want more information on how this works, you can go to this reference over here, Appendix C5. I will release this out after this talk so that you can have these links to click on, and if you're interested in any of this, you could look through it. So now to get on with the results and the analysis. So let's first define what error is. So the error in the simulation will be the delta B simulated minus the delta B observed. So it's just the simple difference between the two. A negative result will mean it's underestimating, and a positive result means it's overestimating. And these manifest in normal curves. So over here, I'll show you some results. So what are we looking at here? This is quite a few figures. So the top are high latitude stations. The bottom are mid latitude or equatorial region stations. On the left, I show just one station, which is Yellowknife in Canada. On the right, I show a combination of all the high latitude stations. And on the bottom left, this is the magnetometer station in Boulder. And in the bottom right, it's a combination of all mid-latitude or equatorial region stations in combination. And what's most interesting here is the green line. That is the horizontal component of the magnetic field perturbation. That just means it is a magnitude between the north and east components, and it's always a positive number. So it's easy to tell whether it's overestimating or underestimating. You can see that these curves have a median of about 0, which is good, which means we're simulating most of it right. These gray regions over here are the interquartile ranges. And it seems like in the lower latitudes, the simulation has a tendency to underestimate because it becomes more negative. And in the higher latitudes, the simulation seems to overestimate. So these are things to keep in mind if we're using the SWMF to forecast. So SWMF has a tendency to underestimate, especially in the lower regions, and the median is around 0. So another way to analyze these is to look at the Heidecke skill scores. So what's the Heidecke skill score? So you set a threshold value, and like some sort of signal or event, and you count both the simulation and observations. So both simulation and stations are above a certain threshold value, which you've already picked. You call that a hit, as in they both agree this is a true positive. If both the simulation and the station are below that threshold value, then that is correct, and that is a true negative. And if they are in disagreement, we could call that a miss or a false positive in our case. And a combination of these gives you this equation, which is the Heidecke skill score. So the Heidecke skill score is a proportion, or the best way to explain it in simple terms, it's the proportion correct by the proportion by chance. As in, if you get a 0 or a negative number, it is not much better than randomly picking numbers and checking through the threshold values. So between negative infinity and 0, that's what that means. Between 0 and 1 means you are doing better than random, and that is the goal, is to get a number closer to 1, a positive number closer to 1. So we choose a threshold of 50 nanoteslas, for example. Why 50 nanoteslas? That's because that was our original criterion on geomagnetic storms, right? That it has a DST or SIMH of less than negative 50 nanoteslas. So we get really good results. So this is an equal area map, of the globe, and all the magnetometer stations are over here. And we get a median Heidecke skill score of about 0.45, which is a good result. This is much better than by random chance, right? So what we can say is, especially in the equatorial region, we get pretty high results, and we can use SWMF to predict results over here, or to forecast results for these ground magnetometers. There is, and it's hard to see here, but I will show later, there's a dip before and after the auroral region. So this is geographic coordinates, of course, because I have this overlay over here of the of the land. So this would have to be in geographic coordinates. And before or after the auroral region, you can see that the numbers become smaller around 0.2 before bouncing back up to 0.45 median. So that's a very interesting result that comes out of this. If we put up a higher threshold, so this is a threshold of 200 nanoteslas. Why 200 nanoteslas is because when you go to the high latitudes, right, you're more interested in auroral electrojets, and they have larger delta Bs. They have delta Bs that are over 200. They can go to 1,000 sometimes. So that's what we're interested in up here. So this is the high latitudes. And we can see here that the auroral regions have very good results, but once we go south or north, they dip. And these would make sense since there aren't that many results that are greater than 200. So that's why we can get zeros closer to the equator. And we get a median Heidecke skill score of 0.32 for this threshold. So now here's a plot of the magnetic latitude by Heidecke skill scores for all stations. So this is magnetic latitude, and this is the different thresholds. And I have error bars on this, and you can see they're pretty tight. This is a 95% confidence interval for the Heidecke skill scores. And as I've mentioned before, with a threshold of 50 around the equator, we get the best results. There's that trend over here, and that's good for predicting DST. And there's this, in the gray shaded region is the auroral region. It's between 60 magnetic latitude and 70 magnetic latitude, which is what I chose. And you can see that there's a dip before and after. And this is very interesting. And we could make improvements on the model based off of knowing this, because there are a lot of magnetometer stations here that we would like to improve on. And for a threshold of 200 nanoteslas, you can see that the results in the auroral stations are good, but there's a dip before and after. So what does this mean? We can use magnetometer stations to make, or at least predict whether the thresholds will be higher for certain magnetometer stations. And we can use the same configuration that the Space Weather Prediction Center is using right now. And because we have access to faster computers and that sort of thing, stations themselves can do these runs and get these results to predict for themselves. And the auroral modeling works very well, but for certain latitudes, like above and below the auroral region, and those could use improvement. We can simulate these events with physics-based models, and also we can validate or perform statistics like these. And if we're doing model validation, doing validation with this many storms is always a good idea. So we need a big data set. It's easy to do machine learning with big data sets because the big data sets are provided already, but it is possible to do this many simulations, physics-based simulations, before performing statistics like this. And for validation purposes, this is necessary. So for more details, you can check out my paper that's just been accepted for publication. So this is the link over here. Again, I will send this out after this talk, or if anyone that's interested. And any questions?
Great. Thank you. So the question that we have is from Eric. So it's about the Heideck Q-score dependence on choice of your threshold. Do you want to make more comments on that?
More comment on the choice of my threshold. So why I chose 50?
Yeah, have you systematically studied how your Heideck Q-score depends on the choice of your threshold?
Oh, yes, I have. So I have done that study, and this is a good middle of results. This is close to the average signal you get for the high latitudes, which is why I chose this. And also, you'll have to think about how many actual signals we get if we choose a higher threshold or a lower threshold. Because a lower threshold than 200 nanoteslas wouldn't be very fair, because most stations can do that. The simulation can do that too. A higher threshold than 200 nanoteslas, you'll get much fewer results, and you wouldn't get very representative Heideck skill scores. For the 15 nanotesla one, this is basically because of the criterion used to pick the storms. However, the around 50 nanoteslas is mostly the same, because SWMF is really good at figuring out whether the stations are getting a value above 50 or below 50. So around 50 nanoteslas, it's mostly fine. The thing is, above 100 or above 200 nanoteslas, we won't get much results on the equatorial region ground magnetometers. So that's why these were picked for these two cases. Any other questions? I cannot see the chat, unfortunately. So
the other question is from Mustafa. How the results depend on the storm strength?
How does the results depend on the storm strength?
Yes.
So So I have not parameterized with the storm strength. That's something I can definitely do next. The storm strengths are greater than negative 50 nanoteslas, and the range there isn't very high. So the storm strength is actually pretty uniform in some way. Like once in a very long time, you'll get a storm that's negative 200, but between negative 50 and negative 100 is the range we're looking at here. And to parameterize that would mean it would be difficult to bin with these 100 storms.
Okay, thank you. Any other question? We still have time for questions. Yeah, from George. DBDT is of the importance to electrical grids.
Yes.
On the surface of the Earth, is there a plan to expand the work to the Earth's surface?
So these are ground magnetometers on the Earth's surface. The results are Biot-Savart integrals using data from ionosphere. But as we see through the Hierarchy skill score results and the error results, we see that they're pretty close. So I'm unsure. Like we can't have MHD up to the surface, right? But what the surface gets is the results from the Biot-Savart integral. Now, the important thing is the ground conductivities, right? So the conductivities can change on the ground, and that could explain why some of these have bad results, for example, is because there's maybe like mountains or oceans next to them, and that could affect, and that's something we're not simulating. We're not simulating the ground conductivities in that sense. However, ionospheric delta Bs are represented on the ground mainly. Remember, we are using the equatorial regions to find SimH, which is a measure of the ring current, for example. So what we're measuring on the ground is representative of what we're measuring in space.
Okay, so in the same way, I have a question. The surface model for conductivity is something that is it's intrinsic for each station, right? It takes some local features. Is that right?
So that's not necessarily what we're using for this, but I'm sure those models exist, but it would be difficult to use that for the ionospheric potential solver because we're talking about the ionosphere specifically, right? And if we choose ground conductivities for that, we will not get good results in that sense.
I see.
Yeah.
So my following question was possible to extend this simulation for places where there is no super magnetometers.
Yes, and that's what the Space Weather Prediction Center is doing. So, like, some of these places don't have ground magnetometers. So this is there is a you could have the entire results, but I specifically picked ground magnetometer locations and compared with the observed data.
Okay, and I have a comment from George. You might be able to get power companies interested in funding part of the work. It always great, I believe.
Yes, that is something we're looking into. I think Howard had their hands up.
Yeah, Howard Singer wants to say something. Yeah, you can unmute and speak. We have time.
Yeah, thank you very much. First of all, a very nice talk. Thank you for that. And I just wanted to mention in response to one of the other questions, that we are experimenting with using the output of this model, the delta Bs that are coming out, combining that with ground conductivity models and coming up with the geoelectric field, which drives geomagnetically induced currents. So that is proceeding. And of course, all of this work with regard to validation and understanding how models can be improved is really essential to that whole process.
Thank you, Howard.
Okay, great. Thank you. Okay, I think, yeah, it's time. Thank you very much.
Thank you so much.
Thank you, Qusai. Thank you, Frankie. Both are very nice talks. One announcement, we have no seminar on the next Monday. Is supposed to be November 14. So we will inform you when our next talk and the title and the speaker. Thank you all. Thank you very much. Have a nice week. I hope see you guys soon.
Yeah.